We're going to recall that we have several statements. We have a conditional. This is the original statement. If P, then Q. P would be considered the hypothesis, and Q would be the conclusion. Hypothesis comes first, conclusion comes second. That's represented by P arrow Q. The arrow here represents the phrase if then, or the two words if then. The inverse, or the opposite meaning, would be the if not P, then not Q, or the opposite of P, shown by the tilde, then the opposite of Q, again, shown by the tilde. The converse statement would reverse the letters. So if Q, then P. Notice that the letters have been reversed from the original or the conditional statement. The statement is kind of flipped. The contrapositive is both opposite, like the inverse, and flipped, like the converse. So that would be read, this symbol here would be read, if not Q, then not P, or the opposite of Q, then the opposite of P. The last one, the biconditional, is essentially one that goes both ways. If P, if and only if Q. This phrase, if and only if, is represented by this double-headed arrow, representing the fact that the statement runs forward and backward. You still maintain the hypothesis letter in the front and the conclusion letter in the back. The word and or also have symbols. P and Q would be represented by P upward caret Q. You might remember that that's the beginning of the word A, or the letter A in the word and. You just have left out this middle part here. The word or is represented by the opposite symbol. It's almost like a V. You might think of it as like a really weird R, perhaps. The laws of logic. You have a detachment and a law of syllogism. The law of detachment gives us only one statement. P, if P, then Q. It then separates the hypothesis and says, you have P. These three dots mean the word therefore. That identifies a conclusion is about to occur. So therefore Q. This is a valid argument because P comes first and Q comes last. You have P, then therefore you have Q. The law of syllogism essentially links several of them together. The first statement says if P, then Q. The second statement says if Q, then R. Notice that the conclusion of the first one becomes the hypothesis of the second one. The third statement in this case is going to be the conclusion. We know because you have the phrase or the symbol therefore. P, if P, then R. To make a conclusion, essentially you discount or wipe out the middle people, the Q and as the conclusion of the first sentence and the hypothesis of the second, which would leave just P leads to R, or if P, then R, which is what you have here. Remember this, the contrapositive is true when the conditional is true. So if the contrapositive is true, then the conditional is true. If the conditional is true, then the contrapositive is true. It also works for the converse and inverse. If one is true, then the other is true. This is an example of a detachment using a contrapositive. If P, then Q. Not Q. Well, remember, what this statement said here is that if the contrapositive is true when the conditional is true. Here you have a conditional statement, which means also you have a contrapositive statement which is true. So if you know that P leads to Q, then you also know that not Q would lead to not P. Notice that this statement is the not Q, therefore not P. That would mean that this argument would be valid. This is an example of syllogism using the contrapositive. All right, so again, you have if P then Q, if Q then R. Statement number 1 and statement number 2 would combine to create if P then R. We've left out the middle Q. That's the conditional. Or what you could know based on this fact that the contrapositive is true with the conditional is true, you could reverse it and negate, saying not R, then not P. Both statements, the conditional and the contrapositive, are true at the same time. Well, going back to the argument, in the third line of the argument, therefore not R would lead to not P. That matches what we created here, and so we know that this argument is indeed valid. Counterexamples. These are specific examples which prove a conjecture or a theory based on observed patterns wrong. It only takes one counterexample to disprove a conjecture. All right, let's work some examples. Consider the following statement. If 4x equals to 8, then x equals 2. Which is the inverse of this statement? Remember, the inverse means the opposite. Here is the inverse reminding you of the opposite. All right, so we're looking for the opposite of this. Well, what it would be is the opposite of this meaning would be 4x does not equal to 8, then x does not equal to 2. The first one, option F, is if x equals to 2, then 4x is not equal to 8. Notice that these parts are reversed and this is changed. So this isn't actually any of our statements. If x does not equal to 2, then 4x does not equal to 8. Well, these are both negated, but notice that the second statement and the first statement are reversed. This would be a contrapositive. If x equals to 2, then 4x equals to 8. Well, nothing has been negated, so it's not the inverse, but notice that the statements have been reversed. This would be the converse. Lastly, 4x does not equal to 8, then x does not equal to 2. That's what we have, the opposite of the first, the hypothesis, and then the opposite of the conclusion. So our solution here, or our answer here, is J. In this example, use deductive reasoning. If the first two statements are true, then which third statement is invalid? Invalid means does not follow the pattern. Well, statement number 1 says if P then Q. Statement number 2 says if Q then V. And remember, in this case, we can eliminate the middle letter, so we would know that we might have P arrow V, or we might have not V arrow not P. I see therefore not V leads to not P. We know this is valid. Let's look at a different example. P leads to Q, or if P then Q, if Q then not V. Here again what I can do is eliminate these two, and I would know that I would have if P, then I would have not V. The contrapositive of this, which would also be true, would be the opposite of not V, or V, then not P. Either one would be valid. I have therefore V leads to P. Well, this doesn't match either one of my statements, so this would be invalid. Here I would have P leads to Q, and then Q leads to V. I can eliminate this middle letter and create my own conditional statement from this. P leads to V. The converse, or sorry, the contrapositive, which is also true, would be the opposite of V, leading to the opposite of P. Here is my conclusion. P leads to V. That matches my original. This is valid. Finally, not P leads to not Q. Not Q leads to not V. Again, what I can do is I can eliminate the middle part, and I know that not P would lead to not V. That would be my conditional statement. Or, writing the contrapositive, reversing and negating, V would lead to P. Therefore, in my third line here, this is my third line, not P would lead to not V. That matches my original, so this is indeed valid. And we want to know the invalid statement, so B would be an invalid statement. The first statement and the second statement do not follow with the third statement. Invalid. This is a question about counterexamples. Counterexamples. I see the classroom floor is covered in brown tile. Therefore, all of the floors of the school must be covered in brown tile. That's the conjecture. I make an observation on a pattern, and I come up with a theory. Which of the following could be counterexamples? All right. Well, A says the gym floor is wooden boards. Well, that is a part of the floor of the school, and it's not covered in brown tile, so that could be a counterexample. B, the hall is tiled in blue-gray tile. Well, again, the hall is part of the school, and it's not brown, so that could be a counterexample as well. The main office's floor is carpeted. Again, part of the school, and not tile. D, the parking lot is black-topped. Here, this parking lot is not part of the school. So it doesn't matter what it is not a valid counterexample. So you have three possible counterexamples. This last one in the examples is practicing writing symbolic notation. If P, the letter P, represents yams are orange, and Q represents rocks are round, write the symbolic notation for the following statements. Yams are not round. So this would be the opposite of yams are round. So this would start off as not P. If and only if. Remember, this phrase here is represented by the double-headed arrow. And then lastly, rocks are round. That's the same as Q, so I would have not P, if and only if, Q. Just an example. Yams are orange. That's straight up what P says. So I've got P. That's what this part is. And. Well, I've got my word and. I need to remember that that's going to be a symbol that starts off looking like an A. Rocks are not round. It's the opposite of the meaning of Q. So I'm going to use tilde Q. Rocks are round. Well, that's Q. Or, again, my word or here, should switch colors, is going to be the upward facing V. That's going to be what the word or shows up as. Yams are orange. Well, that's going to be what P represents. Okay, the third one and last one, if rocks are not round, then yams are orange. Well, I've got the whole if-then meaning, so it's going to be an arrow in the center, a one-directional arrow. The hypothesis here would be rocks are not round. It's the opposite of Q. So I'm going to have not Q leading this statement. Yams are not orange, which would be the opposite of P, so the opposite of P. That would be the symbolic representation of this last statement. Thanks for watching.